Hello, everyone. We are Tina and
Henrik, and today we are talking about green programming.
we prepared this presentation to be 1 hour and not 75 minutes. So we will have some time for questions afterwards. Thank you all for coming spontaneously to our talk. If you want to follow along the slides during the talk, maybe you cannot see very well, you can download them from here. We also shared the link on Discord.
This talk is split into three major chapters. We will start with a general introduction into the rising problem of energy consumption. Afterwards, we will define the term green programming and move on to green software programming.
Then we will present the algorithm we are going to use to create our own measurements, the results, and share an evaluation based on our findings. Lastly, we will go over some tools, other environmental aspects, possible steps you can take if you want to go greener with your product, and in the end, our conclusion. The worldwide energy consumption is on the rise. There are many reasons for this, like economic growth, industrialization, population growth, urbanization, increase of living standards, climate change, and also technological developments and digitalization. With the technological development comes an increase of the number of data centers.
According to Goldman Sachs research, data centers worldwide consume about 1 to 2% of overall power, rising to 3 to 4% by the end of the decade. The workload of data centers nearly tripled between 2015 and 2019. During this time, the data centers' demand for power did not change because the data centers themselves grew in efficiency. But since 2020, the power consumed by data centers worldwide has risen, with AI being one of the main reasons.
The spread of AI and machine learning requires enormous computing power. These are technologies, as these technologies process large amount of data and perform complex calculations. The training phases of AI models are particularly energy intensive. Goldman Sachs reports that a single ChatGPT query requires about 3 watt-hours of energy compared with 0.3 watt-hours for a single Google search. This is an increase by a factor of 10. They also estimate that the overall increase in data center power consumption from AI will be in the order of 200 terawatt-hours per year in the year between 2023 and 2030. By 2028, the analysts expect AI to represent about 19% of data power demand.
But not just AI drives energy consumption. We will take a closer look at the other driving factors as well, like the increase in data traffic. With the digitalization and growth of the internet, the data traffic has increased massively. We have streaming services, social media, cloud computing, online games, and the general use of the internet, which generates enormous amount of data that need to be stored, processed, and transmitted. Data centers are the backbone of these activities and require significant energy to handle the increasing data traffic.
Growth of cloud services. More and more companies and private individuals are using cloud services for processing and storage. Cloud platforms such as Amazon Web Service, Microsoft Azure, Google Cloud host millions of applications and websites, driving up the energy consumption of their data centers.
Blockchain and cryptocurrencies. The spread of cryptocurrencies such as blockchain has greatly increased energy consumption in data centers that carry out so-called mining operations. Mining requires a large number of computing operations, which are carried out in specialized data centers with specialized hardware.
Increased availability and redundancy requirements. Companies and organizations are increasingly demanding higher availability and resilience of their IT services. To meet these requirements, data centers operate redundant systems and storage capacities, which increases energy consumption.
Cooling requirements. Data centers generate considerable amount of heat from their servers and other IT equipment. To ensure trouble-free operations, they need to be cooled intensively, which accounts for a significant proportion of total energy and also water consumption.
Exponential growth of network devices. As the networking of household appliances, vehicles, machines, and other devices processes, the amount of data to be managed and processes also increases, requiring more data centers, and therefore more energy. So we see IT and software have a huge impact on the worldwide energy consumption. This means that this is a topic that we should all have in mind when creating new software, because there are things that we can influence.
Now let's define what green software is. Firstly, this is a huge field. We use the definition of green software from the Green Software Foundation. With green software, we want to focus on reducing carbon emissions. This can be done by focusing on using fewer physical resources. For example, if you create new software that requires users to upgrade their hardware, this will create more carbon emissions. Long gone are times when a hardware product was designed for life, or even a 10-year lifespan. Nowadays, we live in an economy that wants you to update your hardware every year. The production of new hardware alone uses a lot of energy and other resources. We should aim to go back to longevity of products, even if that means losing out on profits.
Using energy more intelligently. This means consuming lower carbon sources for your energy, or consuming electricity in a way that helps accelerate the energy transition towards a low carbon future. For example, there are data centers that run on renewable energy. We will go into detail in this topic later. Using less energy. This means that the software you produce uses less energy. This can be influenced by the programming language you choose. In this talk, we will focus about using less energy by choosing the optimal programming language for your purpose. If you want to find out more about the Green Software Foundation, we have linked the organization here. They are split into 4 different working groups. The Standards Working Group, which focuses on defining baseline specifications for green software. The Policy Working Group, which focuses on the foundation's trademark and where it can be used. The Open Source Working Group, which focuses directly on the open source, open data, and research community, and help guide them into a more greener software field. And the Community Working Group, which focuses on creating partnerships, content, events, and programs. They also have a huge repository on material related to this topic. This includes tooling, organizations, courses, and research material.
There's also the Sustainable Digital Infrastructure Alliance. Their vision is to drive change at the foundation of the digital economy, its physical infrastructure. They focus on achieving a regenerative digital economy by leveraging innovation, collaboration, and policy advocacy. They want to create a digital infrastructure that is not only efficient and resilient, but also in harmony with our planet's ecological boundaries. Check out their website and roadmap for their sustainability goals by the year 2030.
One last one. If you're a gamer or you work in the gaming industry, you might find the Playing for the Planet Alliance interesting. They are supported by the United Nations Environment Program, UNEP. Sustainability in the gaming industry is their main focus. They help companies in the video game industry to reduce the carbon footprint. Therefore, they offer guidance and tooling like a specialized carbon calculator. An annually event organized by the organization is called the Green Game Jam. It challenges game developers to integrate green activities like raising awareness about environmental issues into their games. And in 2023, famous companies like Rovio, Gameloft, and Tencent participated in the Green Game Jam.
Also, at last year's ECU conference, there was a talk about this topic called Green Software Architecture by Giovanni Asproni. He talks more about the environment of where the software runs and how the software is structured. He briefly mentions the programming language issue that we are talking about in this talk. This is a really good talk to get an overview of many different aspects of green software as well.
As I said before, we are going to focus on the programming language part of the green software topic.
Green programming or green coding is a series of principles applied to software development that aims to reduce the ecological footprint of software. The goal is to write energy-efficient code, use resources economically, and use environmentally friendly technologies to reduce the CO2 footprint. This can be, for example, influenced by the programming language you choose. Which brings us to the research paper named Energy Efficiency across programming languages by various authors, which this talk is inspired by.
This paper presents a study of the runtime memory usage and energy consumption of 27 well-known software languages. They monitored the performance of these languages using 10 different algorithmic problems programmed in each of those languages. The results show the speed of the programming languages, the energy consumption, and how it is influenced by memory usage. They also show how to use these results to provide support to decide which language you want to use if energy efficiency is a concern. These are the algorithms they tested and the programming languages they used. The languages are divided into the categories functional, imperative, object-oriented, and scripting.
And these are the results of two different algorithms for all the programming languages. The algorithms are Funko Redux, which is an algorithm which calculates the maximum number of flips to sort an integer sequence consisting of a permutation, and FASTA, which is an algorithm about random DNA sequence generation. As you can see, and unsurprisingly, the tables are led by the languages that are compiled directly to machine code. Although the most energy efficient language in each benchmark is almost always the fastest one, there is no language consistently better than the others. The paper also analyzes if maybe the memory consumption has an impact on the power consumption, as the fastest languages also use the least amount of memory, but found no correlation. It seems like runtime is the biggest factor of energy consumption. We provide a link to this paper in the sources section of this slide deck if you want to check it out for yourself.
Now we see if we can replicate these results. We want to analyze for ourselves if we can find best practices for green programming. We look for an algorithm that is easy to implement in different languages, but complex enough to actually measure something. Additionally, the algorithm should not be standard so that there's no highly optimized library function for that, like sorting. We decided to go for two small functions, the Monte Carlo simulation to approximate pi and the adver32 algorithm to calculate checksums. We will start with the Monte Carlo simulation to approximate pi to compare the speed of the different programming languages.
Monte Carlo methods are a class of algorithms that rely on random data to approximate numerical results. They are mainly used in optimization, numerical integration, and generating draws from random distributions. Monte Carlo methods are used in various fields of science, engineering, mathematics, physics, chemistry, biology, statistics, AI, finance, and cryptography, even in social sciences like sociology, psychology, and political science. How does the Monte Carlo approximation of pi work? We have the first quadrant of a unit circle and a unit square. Then we generate random points inside this quadrant with uniform probability and count how many of them are inside the circle. Pi is then approximately the number of points inside the circle divided by all points times 4.
When we do that for 1,500 points, pi is around 3.09. For 5,000 points, pi is around 3.13. For 50,000 points, pi is still around 3.13, so there's not a big change here. So we go to 10 million points, now pi is around 3.14, and now we're getting close. For all the measurements with all the programming languages, we will use 10 million samples.
To implement this, we need to first specify how we want to generate the random numbers. We use the standard random device, default random engine, which is the Mersenne twistor engine, according to the C++ standard, and a uniform real distribution from 0 to 1. Next, we have a for loop until we reach the number of iterations. We don't need the looping variable here. Within the loop, we generate random x and y coordinates. These will form the points. If the points are within the circle, we increment the counter variable. In the end, we return 4 times the number of points inside the circle divided by the number of iterations, which is the number of all points.
So if you know me, you know when I see a loop, I'm going to rangify it. So the beginning of the function is the same. We still need the random generator, engine, and uniform distribution. For the for loop, now the for loop can be replaced by an iota view. We use the transform view and discard the loop variable. Within the lambda of the filter view, we generate the random numbers and check if the points are within the circle. To count the number of values within the circle, we use range as distance, and then we return the approximated pi value. We implemented this algorithm in 12 different programming languages, and this is the Python version.
Adler32 is a simple algorithm for calculating checksums based on the Fletcher checksum. It was invented by Mark Adler and is, for example, used in the zlib library. The input of the algorithm is a byte vector, and the result is a 32-bit integer, which is made up from two 16-bit integers. The parameter a is initialized with 1, and in each step the value of the next byte to be checked is added up to it. The parameter b is initialized with 0, and the current value of the parameter a is added up to it in each step. Both sums are calculated modulo 65,521, which is the biggest prime number that is smaller than 2 to the power of 16. The result will be the combination of the two 16 bits of b and a into a 32-bit integer.
So now, of course, the real question is, where's the range? And the range is in the sum of b, which is an accumulate, or in C++23, a fold left. So this is the rangified version. It gets rid of the for loop, and it also makes b cons, which I think is a big plus. We implemented this algorithm also in 12 different languages, and here's the Python version again.
If you want to review all versions for all programming languages, you can go to our GitHub using the QR code on the bottom right corner here. We uploaded all the code examples and the code to reproduce the results there.
Now that we know which algorithm we want to use, we need to talk about the rest of the experimental setup. What programming languages do we want to use? How can we measure energy consumption of the relevant components like the processor and the RAM? And how are CO2 emissions calculated? One of the many ways of categorizing programming languages is to look at how they execute code. Some languages like C, C++, or Rust are compiled to machine code directly, which is then executed by the processor. They also hand over the management of the program's memory to the developer. These things are often believed to create the fastest programs. Other languages like Java compile to bytecode, which is then executed by a specialized virtual machine. It may figure out what passed during runtime and optimize the bytecode accordingly. These languages usually manage memory via garbage collection so that the developer does not need to take this into account.
Some other languages like Lisp are interpreted line by line. We want to include at least one language of each category, but we found out that Lisp is too slow in comparison and left it out in the end. If the execution of the program involves additional components, which are run alongside the program, these components will also consume energy. This can be the case for a garbage collector, the VM executing the bytecode, or an interpreter. We use the programming languages which you can see here on the slide. It is a good mixture of the different categories of programming languages we just mentioned.
All languages receive the exact same data as input to execute the algorithms. The languages differ in their calculation, memory management, and how their standard library is implemented. The algorithms are using different built-in functionalities of the standard library, like generating the random numbers. For C++, we also looked into two different implementations, one with standard ranges and one without. We thought it might be interesting to see if we get different results using different parts of the standard library.
Everything is executed on a machine with an Intel Core i7 processor and 8 gigabytes of RAM. The computer is a Windows machine, but the code is executing within this Windows subsystem for Linux. All programming languages receive the same input, which are 10 million iterations for the Monte Carlo pi approximation and 50 megabytes of random bytes for the Atlas 32 checksum. This is hard-coded into the source code. No file access or network communication is done. The only I/O done is printing the results to the console standard output after the calculation has finished.
We use the Code Carbon Python package for tracking and calculating the energy consumption and CO2 emissions. We run all examples for the different programming languages from one central Python script and measure only the execution time. The compile step is not part of the measurements if there's any. Code Carbon can track the energy consumption of RAM via an assumption of 3 watts per 8 gigabytes of RAM used. The CPU is measured by the Intel Power Gadget for Windows or via the RAPL files for Linux. If you're running a Mac with Apple Silicon chips, the Power Metrics tool is used for tracking.
If none of these is available, Code Carbon will look up the processor in its database with over 2,000 Intel and AMD CPUs and retrieve its thermal design power or TDP. It will then assume a constant energy usage, which is 50% of the CPU's TDP, which is an empirically tested value coming from the authors of Code Carbon. The GPU can also be tracked and measured directly for NVIDIA GPUs. This is done via the PyNVML package. Note that we did not do any programming for the GPU and do not measure GPU energy consumption. For estimating the CO2 emissions, the energy consumption of a program is used together with a database of energy production mixes for different countries. Your geolocation is determined automatically for this calculation. Monitors and other periphery, of course, consume energy as well, but are not considered by Code Carbon. We rely on a single Python script which compiles and executes all languages in one place for convenience reasons. Only the execution time of the algorithm is measured.
This is done by using the emissions tracker context manager in the example above. All code within a context manager is measured, and Code Carbon will automatically figure out how to measure CPU, RAM, and GPU energy consumption. With these values, it will calculate the CO2 emissions based on your current geolocation. After the Python script is finished, Code Carbon will create a single CSV file with all the measurements. If you have several different measurements, it is a good idea to give them names. This can be done via the project name argument in the emissions tracker. You can also just measure already compiled programs in Code Carbon. We choose to put the compilation step here into one single file just for convenience reasons. It makes rerunning the entire example easier when we change the code. There's also an alternative to the emissions tracker, and it's called the offline emissions tracker. This will not automatically determine your geolocation, which means you have to provide it yourself using a ISO code for your country.
This can be useful if you want to see how your carbon emissions would change by moving your application to another country. For the USA and Canada, also states and provinces can be supplied for more fine-grained results. If you are using a Google Cloud or are interested in its carbon emissions, you can also provide the Google Cloud region alternatively, and you will get the greenhouse emissions data, especially for that Google Cloud region, coming from official Google data. Code Carbon uses the carbon intensity, which is emissions per power, which is usually measured in kilograms CO2 per megawatt hour, for a country, which is published on the scientific online publication Our World in Data for its calculation. But what does this data consist of?
In order to estimate the carbon intensity for a country, information on the energy sources is needed. Code Carbon uses this table shown on the slide for their explanation of their methodology. The emissions tracker for fossil fuels comes from the US Environmental Protection Agency. Data for the renewable energy sources was obtained from the report Comparison of Lifetime Greenhouse Gas Emissions of Various Electricity Generation Sources from the World Nuclear Association. This is an international organization representing companies from the nuclear industry. You might be wondering why things like solar and wind have a non-zero carbon intensity because they do not emit CO2 in their process of generating power. This is because this data here also considers the non-operational carbon emissions from their construction. With this table, we can understand how the CO2 emissions for a country can be estimated by using their energy mix.
Let's have a look at the German energy mix for the year 2023. In the bar plot, you can see that the energy that was produced in that year in terawatt hours for different energy sources. Low carbon intensive sources make up about 45% of all energy, resulting in a carbon intensity for Germany overall of 380 kilograms CO2 per megawatt hour. For example, Norway has a completely different energy mix, which is dominated by hydroelectricity, yielding a much lower carbon intensity of 30 kilograms CO2 per megawatt hour. Here in the UK, the energy mix yields a carbon intensity in between Norway and Germany with 238 kilograms CO2 per megawatt hour. On the previous slides, we looked at the energy mixes and CO2 emissions for the public power grid. This is the energy mix we use on average.
Some companies publish more detailed data on their CO2 emissions. For example, Google has a dedicated website where you can look up the carbon intensity and the percentage of renewable energy used in each of their cloud regions. They also mark low CO2 regions in the table if you decide to help you decide where you want to host your cloud service. They also offer the possibility to automatically select lower carbon regions to create a new cloud resource. Amazon releases global carbon footprint and their information of which of their regions run on 100% renewable energy. But no individual carbon intensity per region is given. Instead, you can access a dashboard with your personal CO2 information in your AWS account. Microsoft offers a dashboard for Power BI, which calculates and visualizes the greenhouse gas emissions for your Azure cloud usage.
Now that we have shown you the setup and what we use for measuring energy consumption and CO2 emissions, we are going to look at the results for both the Monte Carlo Pi approximation and the Adler32 checksum. For visualization purposes, we normalized energy consumption by dividing all measured results by its overall minimum value, yielding one normalized energy unit. All upcoming slides will use this unit, which is calculated individually for the Monte Carlo Pi approximation and the Adler32 checksum. In the table above, you can see the actual values in kilowatt hours and the associated CO2 emissions estimated by Code Carbon for Germany, that's where we are from, the UK, for obvious reasons, and Norway, because they use a lot of renewable energy.
The decision of choosing where your code is executed can have a huge impact, as you can see in these numbers. Without changing a line of code, just by moving from Germany to a data center in Norway, the CO2 footprint of your code could be diminished by a factor of 10. Here are the results from the measurements of the Monte Carlo Pi algorithm for all programming languages that we showed. In this plot, you see the normalized energy consumption for each program measured by Code Carbon. Just by looking at the bar plot of the results, you can see that the compiled languages with manual memory management uses the least amount of energy, while Python uses the most energy, followed by C#, which both running a VM and a garbage collector.
Looking at the exact numbers, we see that C, Rust, and both C++ variants, with ranges and without ranges, are very close to each other. In most other experiments of such kind, C is usually the best language, but we have also to take the accuracy of the measurement into account here. Repeating the experiment shows that the numbers can vary by up to plus minus 0.5 after normalization, which means that basically all results within that range cannot be distinguished well from one another. If we go beyond individual programming languages, we can find general trends for the categories of programming languages. Compiled languages with manual memory management consume the least energy. There's a large variation within the VM-based languages like Java, Kotlin, Python, and C#. Looking at the numbers, we see that the choice of programming language can influence the energy consumption of your code by a huge factor.
The total energy used is dominated by the CPU. The smaller component is the RAM. C++, C, and Rust have the smallest energy footprint for RAM, while Python has the highest one. The deviations here are interesting because all languages receive the exact same data and therefore store the exact same intermediate results. So the difference here can only come from the way the languages store and manage memory.
Here are results from the measurements of the Atlas 32 checksum for all programming languages we showed, except for Elixir, which didn't work out well in the end. In this plot, you see the normalized energy consumption of each program, again measured with our methodology by Code Carbon. The results are very similar to what you see for the Monte Carlo pi approximation. Again, the compiled programming languages with manual memory management clearly use the least amount of energy, while Python uses the most energy.
Again, the RAM plays a smaller role in the total energy consumption. The CPU makes the largest part of it. In this experiment, RAM energy consumption is different for the individual languages as well. Compiled languages tend to consume less energy for storing the same amount of data compared to the VM-based languages.
And what can we learn from these results, and what can you do to improve the energy and CO2 footprint of your software? The results show that different programming languages have vastly different levels of energy consumption and therefore CO2 usage for the same algorithm and the same dataset. In our case, this was mainly influenced by the execution time and a little bit by the memory usage. But the results may differ a lot depending on your actual algorithm you want to analyze. We looked at a program with a focus on computations, without any kind of I/O like network or file communications, and we also didn't use the GPU.
As it is shown in the paper we discussed at the beginning of the talk, the smallest energy footprint is achieved by languages which compile to machine code and do manual memory management. In general, it doesn't seem to matter which one of these compiled languages you choose if you want to reduce your CO2 footprint. In the end, it comes down to the purpose and what you're most comfortable with. Energy efficiency of a program also comes from good optimization. For example, it would not bring you much runtime speed if you would compile C++ without any optimizations. C and C++ also profit from highly optimized compilers, which are worked on for decades now. And there are more specialized compilers as well, like the C++ Intel compiler, which utilizes hardware acceleration features for even faster programs.
If you look at these kinds of experiments, you might be tempted to rewrite your software in a language which has a better position in such a benchmark, but this is usually not a good idea for two reasons. A rewrite takes time and consumes a lot of resources. It might take a long time until you're saving more energy than you have invested in your rewrite. And secondly, not every programming language is suitable for every task. You wouldn't want to do just database queries in C++, for example. Therefore, the choice of programming language also needs to take the purpose of your code into account.
Instead of a rewrite, you can rely on optimized libraries where the core algorithms are written in a language that are compiled to machine code. For example, in Python, you can use NumPy for array-like operations instead of doing the same in native Python. But keep in mind that this can help improve runtime, but it will never be as fast as using the compiled languages directly. The pros and cons here need to be evaluated from case to case.
Sometimes also different implementations of your programming language might be available. You could, for example, use PyPy as a drop-in replacement for CPython. PyPy is usually more performant due to its just-in-time compiler. Looking at the theoretical runtime complexity of your algorithm and looking for better alternatives is also a good idea. An example here could be different sorting algorithms, which vary a lot in complexity. Also, not every program needs to be highly optimized. If the program is only used by a handful of people twice a year, who cares? That will not make a difference. But algorithmic intensive programs that are executed often will often profit highly from optimizing. We will also highlight some helpful tools. We develop software for desktop PCs, so energy consumption was never an issue for us before. But if you develop for battery-powered devices like smartphones, energy consumption has always been something to optimize for. Now, this is also gaining some traction for other applications. We already discussed Code Carbon, a very useful tool for measuring the energy consumption and CO2 emission of code due to its versatility. But there are more tools.
There's also the Intel Performance Counter Monitor, or PCM, which provides an API and tools to get the energy metrics for a large set of Intel processors. It runs on many operating systems, including Windows, Mac, and Linux. PCM provides a number of command line utilities for real-time monitoring. The basic processor monitoring utility is also called PCM, and this is a tool that you can use that measures all sorts of things, including the CPU and the memory energy consumption.
The ARM Development Studio offers energy profiling possibilities for embedded devices with ARM chipsets. Capturing energy data is part of its streamlined performance analyzer. But the capturing of energy data seems to be deprecated now, according to the official documentation, with no mentioned successor. And lastly, Oaklean is an energy profiling tool for JavaScript and TypeScript applications. It creates detailed measurements of CPU time, CPU energy consumption, and RAM energy consumption for each component of the application. It is integrated into Visual Studio Code and can show the energy consumption directly in the source code, down to the exact line of code or library call. It can also be integrated into your tests. For this, Jest is currently supported.
There are a lot more tools which are specialized for certain programming languages or environments like cloud or Kubernetes. You can find a list in the Green Software Foundation GitHub repository. Now we have talked a lot about CO2 footprint of the software. While greenhouse gas emissions are the main driver of climate change, there is also other environmental aspects of our modern digital world. We will briefly look into water usage of data centers and the environmental costs of hardware manufacturing. First, let's look at the issue of water usage. There are two ways in which data centers can use water. The first one is directly by using water to operate their infrastructure. The production of power in plants consumes water. Fossil fuels and nuclear power plants convert water into steam using heat from their energy source, and the steam rotates a turbine, which then generates energy. Water is lost in this process due to evaporation or discharged as effluent. Also, hydropower plants lose this water due to evaporation from open tanks.
Direct water consumption of data centers is a result of cooling. IT equipment produces heat during its operation. To prevent equipment failure, the temperature in data centers needs to be kept at room temperature or well below. This is usually done by cooling the air using cold water, which results in water loss due to evaporation. Another direct water usage is humidifying the air in data centers, because dry air increases the likelihood of electrostatic discharge, which can severely damage or destroy IT equipment. A study from Virginia Tech estimates that indirect water usage makes up 75% of data center water consumption in the US, while direct water usage only makes up 25%.
Large water consumption can lead to environmental problems because less than 1% of water on Earth is available for human consumption. In the US, data centers are among the top 10 water-consuming industries. There's an incentive to place them in regions where there are lots of solar energy sources, which are oftentimes also regions where water is scarce. They are so-called water stress regions. A Nature study estimates that the percentage of drinking water and direct water usage of data centers in the US was 57% in 2019.
All major cloud providers have stated that they want to be water positives by the year 2030. This means they want to return more water than they use directly. The main ways of doing that are increasing the efficiency of their cooling systems, moving to a lower percentage of fresh water by using more recycled water, and funding water replenishment projects. Our personal contribution to reduce water consumption is the same as for reducing the carbon footprint. By writing greener software, we can contribute to lower the computational resources, which helps reducing direct and indirect water usage. On the other hand, we can also study the environmental reports of cloud providers and make a conscious decision on choosing a suitable data center or cloud provider.
The results of increasing computational demand is that more and more devices are produced and purchased. There are several environmental aspects associated with the production of IT equipment. Firstly, all processes in the chain of production, like mining the raw resources, manufacturing itself, and the transport of the resources to the final equipment, they also all have a CO2 footprint. This can add up to about 1,750 kilogram CO2 for one single server. And secondly, mining for scarce resources has a direct environmental impact due to erosion, loss of biodiversity, and contamination.
Mitigating the environmental footprint of hardware manufacturing also has the same components as water usage mitigation. By writing green software, we minimize the usage of computational resources and help minimize the demand for new hardware. On the other hand, you should again search and study the environmental reports of your cloud provider. There, they will mention their strategies for a circular economy, like recycling, reselling equipment on the secondary market, prolonging the lifetime of equipment, and waste management. Change cannot happen overnight, but there are small steps we can do if we want our software products to be more environmentally friendly. So we also want to share some strategies that you can implement to move to a greener product.
Green software by design. Keep green software practices in mind from every step from the beginning of your product. You can start by educating yourself and your team about green software and bring the discussion directly into a new project. At this time, only a few decisions have been made, and it might be able to implement some of the green software measures. If the product is already in the world, it's way harder to make changes or justify the expense of transforming them.
Green requirements. How can requirements be green or greener? For example, by only requiring what the customer actually needs. Requirement management is a really complicated topic, and trying to figure out what the customer really wants is not easy, but it pays out, not just in saving development time, but also further down the line. Code that has not been written does not need to be compiled, deployed, tested, and maintained, reducing the workload in every step. Also, there's a trend of adding AI to everything, even to remote controls or coffee machines. It's doubtful that this is really what the customer wants and needs. New trendy technology should not be added to everything. Here we need to ask ourselves where this requirements comes from if it's not from the customer.
Rethink the accuracy of stored data. As said at the beginning, everyone and everything collects a lot of data nowadays. The amount of data only grows, which drives the demand of storing the data somewhere. We should rethink if we need all this data and also if we can reduce the accuracy of that data. We have an example for this problem in our company. Among other data, we store wall thickness for pipelines in our pipeline inspection data. The wall thickness is stored in millimeters and the data type is float with a precision of 8 digits. We need to ask ourselves if this precision is really needed. What would it mean to store a millimeter value in a double? There's always the feeling that we need to be as accurate as possible with our calculations, but the numbers have no real value once we go into micrometer or even nanometer precision.
So we always have to ask ourselves which precision is enough, which data type is the smallest that we can use to reduce the overall data. This matters as a single inspection, in our case, can have multiple terabytes of data. And less data means less data to store, copy around, and read in for calculations. This question also applies to data that we store and use within our programs.
There are data centers that run on renewable energy. This is a good start when you want to move to a greener product. As shown before, there are services like the Google Cloud Service, where you can look up which cloud region you want to choose if you want to reduce the carbon emissions. Also, more and more companies install their own solar panels for their energy demands, to cover their energy demands partially or completely. This is an investment for sure, but it will help to move the overall power generation to a renewable energy.
Clean up your code. That can mean the removal of code that is not used anymore, which is a good idea for many other reasons as well. Code that is unused still needs to be compiled, deployed, tested, and maintained. This creates a lot of effort. Keeping code that is unused also contributes to code load. Code load can make the program less efficient and slower. This can also happen when software engineering principles are not applied, like reusing functions instead of rewriting or copying them all over the code base. Another contributing factor is when principles are applied that are not necessary to solve the problem, like using object-oriented design where it's not needed and a procedural approach would have been enough. This is something that we have to keep a constant eye on, as code grows faster than it can be cleaned up or refactored.
Clean up the data. This means that there needs to be a strategy to clean up data, preferably automatically. I think we all know the problem of test systems that write some kind of data to the hard drive, and the data needs to be kept there for a while in order to check the test results. But at some point, this needs to be deleted. Otherwise, the hard drive will be at some point at capacity. There has to be policies for this, because cleaning up manually is a hassle and it can be forgotten. It's so tempting to not want to deal with these kinds of issues and just buy a new storage system if the old one is full, but that's not sustainable. And the new storage, again, will have the same problems and will consume more energy. This is like the cleanup code issue. It has to be constantly worked on in order to not spiral out of control.
And to conclude, worldwide energy consumption is on the rise. This has many reasons, like the acceleration of AI services, especially in recent years. We saw that programming languages which are compiled directly to machine code are the most efficient, and that correlates directly to CO2 emissions. While RAM plays a role, it's not nearly as high and big as the CPU. But there are more things to consider when choosing a programming language, like if it's fit for your purpose. If this topic is important for you, you can use tools to measure the energy consumption of your program, and you can even include this into your testing routine. Water consumption and the need of new IT equipment also contributes to environmental damage.
We also showed that you can already take a lot of small steps in order to have a greener product. While we cannot influence directly how sustainable the energy of our countries is produced, we can aim to do the small steps ourselves. This includes trying to reduce the CO2 footprint of the programs that we write by using efficient languages and libraries. This is our own contribution to a greener future. Thank you.
Thank you.